Welcome back, secondary educators. Now that we have the whole numbers set, it's time for us to take a look at the integers, which are a natural extension of the wholes, and so we do this in a very natural way. An integer is an ordered pair AB, where A and B are whole numbers. And since we've established that whole numbers are a thing, we can talk about an ordered pair of whole numbers AB. Define the equivalence relation tilde in the following way. We're going to say that the ordered pair AB is equivalent to the ordered pair A prime B prime if A plus B prime is equal to A prime plus B. Now, I've got to pause here and do a Math 239 thing. Equivalence relation means that we are reflexive, symmetric, and transitive. You should judge for yourself whether or not this equivalence relation, whether this relation is in fact reflexive, symmetric, transitive. Okay, so I'm assuming that you've paused the video if need be to run those things through in your head. It's fairly straightforward that this relation is in fact reflexive, symmetric, and transitive. It is an equivalence relation, and it's how we judge whether or not two integers are equivalent. If it helps to think about this on a number line, we would say that the ordered pair 2, 4 is equivalent to the ordered pair 8, 10. We would say that the ordered pair 2, 4 is equivalent to the ordered pair 8, 10, right? So 2 plus 10 is 4 plus 8. That's not terribly difficult. Both of these ordered pairs represent the integer 2 for obvious reasons. We think about integers as ordered pairs, the start point and the end point for a vector on the number line. That is a natural way for us to think about integers. It allows us to think about positive integers as vectors pointing to the right, and it allows us to think about negative integers as vectors pointing to the left. The set Z, Zahlen, is the set of equivalence classes under tilde. Well, if this is true, if this is true, if both the blue vector and the red vector represent the integer 2, then the integer 2 is really an equivalence class of all of the possible ordered pairs where A and B are 2 apart, where B is 2 greater than A. So the set Z is not a set of ordered pairs. The set Z is a set of equivalence classes. That's important for you to know. We're not looking at a set of ordered pairs. We're looking at a set of equivalence classes. And so we should ask the question, what does it mean for one integer to be less than another? What does it mean if the equivalence class of A1B1 is less than the equivalence class of A2B2? Well, we'd say that one integer is less than another if A1 plus B2 is greater than A2 plus B1. And I would encourage you to think that through. Pick one integer, make it less than another, come up with a representation for the lesser integer and a representation for the greater integer. See if this holds. If not, drop a comment. We can talk about that. Hope this is helpful for you to see how the integers come to be in a very natural way from the whole numbers, and how we can tell that we can put them in order by equivalence classes.